Look at any supply chain or manufacturing line, and you will eventually find a bottleneck. According to the APICS and ASCM dictionary, managing that specific bottleneck is the foundation of the theory of constraints. The primary objective of this framework is to maximize the throughput of the entire supply chain system, treating the operation as a single continuous flow. This requires abandoning the traditional habit of pursuing local efficiency. Pushing individual workstations to run as fast as possible in isolation doesn't improve the system, it often damages it. This diagram illustrates the three simultaneous operational goals of the theory. A successful operation keeps the throughput gauge increasing, the inventory gauge tightly controlled, and the operating expense gauge minimizing. Adopting these goals forces you to stop optimizing individual parts and start managing the flow of the whole. It is a rigorous systems thinking philosophy, rather than a simple scheduling trick. To apply this philosophy, you have to temporarily set aside traditional accounting metrics and adopt three specific ASCM definitions. This model maps them out. Throughput is strictly the rate the system generates money through actual sales, not production volume. Inventory is the capital currently tied up in physical items intended for sale. Operating expense is the money spent converting that inventory into throughput. Prioritizing throughput over simple machine utilization protects a company's cash flow. Producing goods that cannot be immediately sold does not create throughput. It only drives up your inventory and operating expenses, while trapping your capital. A constraint is formally defined as any factor that limits the system from achieving higher throughput. These limitations fall into three categories. The first is physical. This is the classic bottleneck: a machine with limited capacity, a severe labor shortage, or a supplier who cannot deliver materials fast enough. The second category is policy-based. These are internal business rules, rigid batch sizes, or counterproductive key performance indicators that inadvertently slow down operations. The third category is market-driven, where the primary limitation on your system is simply external customer demand. Every single system has at least one constraint limiting its performance. A manager's objective is not to eradicate all of them simultaneously, but to accurately identify and manage the primary constraint dictating the system's pace. To manage that pace, APICS adopts Eliyahu-Goldratt's sequence, known as the 5 focusing steps. On this circular flowchart, step 1 is to identify the constraint, locating the exact node where flow abruptly stops. Step 2 is to exploit that constraint. This means maximizing the specific bottleneck's output using existing resources, sequencing work so this limiting step never sits idle. Notice that steps 1 and 2 require a complete change in management behavior and operational focus before a company spends a single dollar on new equipment or expanded capacity. Step 3 is the most misunderstood: subordinate everything else. Surrounding non-constraint processes must deliberately slow down to perfectly align with the constraint's pace. Running faster than the bottleneck simply creates massive inventory backups. Next, you elevate the constraint. Only at this stage do you invest capital to add capacity or remove the limitation entirely. Step 5 is to repeat. Elevating the primary constraint inevitably shifts the bottleneck to a new location in the network. Optimization is an ongoing cycle of shifting constraints. Managing them effectively makes continuous improvement a permanent operational state, rather than a one-time project. While often visualized on a factory floor, this framework operates across the entire end-to-end supply chain network. Planners apply it to manage bottleneck work centers in manufacturing, navigate strict transportation limits in distribution, or adapt to long lead time suppliers in procurement. To understand its unique position, we can look at this matrix. Lean focuses on the elimination of waste everywhere. Six Sigma works to release variation across processes. The theory of constraints diverges by applying its focus to just one limitation at a time. The APICS curriculum treats these as complementary frameworks. The theory of constraints provides the strategic map, telling you exactly where to deploy your Lean and Six Sigma tools first to get the highest return on your effort. When implementing this strategy, professionals frequently fall into specific logical traps flagged by ASCM. The first trap is assuming this theory only applies to heavy machinery, forgetting that outdated policies and rigid batch sizes restrict flow just as severely as slow equipment. But the most dangerous misconception is the belief that every process in a facility must be fully utilized in order to justify its operating cost. This flow visualization shows what happens when a high-speed, non-constraint machine runs at 100% capacity. It produces output far faster than the system can process it, creating a massive backlog of inventory right in front of the actual, slower bottleneck. Optimizing a non-constraint creates an illusion of efficiency. In reality, it actively degrades the performance of the overall supply chain by tying up capital in excess inventory. True continuous improvement relies on acknowledging that constraints are inevitable and systematically managing their shifts. As shown on this slide, you can audit your own operations by asking 3 questions. What is your current system constraint? Are your local KPIs hurting system throughput? And what policies are acting as hidden constraints? In APICS and ASCM logic, the theory of constraints does not ask you to fix everything. It demands that you fix the exact one thing that matters most right now.